So far, we have learned many ways to write down complex numbers. Now we are going to see another way to write down complex numbers known as exponential form. Now we shall see that this way of writing down complex numbers will not only improve our understanding about the geometry of complex numbers, but it will also help us in simplifying different operations on complex numbers like multiplication and division. Now, we know that a complex number can be associated with a directed line segment or vector. Now, we know that a vector can be completely specified by its direction and magnitude. So, we can say that we can specify a complex number by this magnitude and direction. Now, the length of this vector can be calculated by using the modulus, and the direction can be calculated by using an angle that this vector makes with positive x-axis. So in other words, if this is the complex number, then this angle theta, which we are calculating with positive x-axis, will tell us about the direction of this complex number. Now these two quantities will completely specify a complex number in plane. So this way of writing down complex numbers is known as polar representation of complex numbers, and r and theta are known as the polar coordinates. Since if z is equal to 0, which is a complex number, if we take z is equal to 0, then the magnitude or the modulus of this complex number is 0, but theta is undefined because this point has no direction. So whenever we talk about polar representation of complex numbers, it is always assumed that z is a non-zero complex number. So the real number, which is the modulus of this complex number, is not allowed to be negative since it is the length of that vector. And the direction which we calculate by angle that this vector makes with positive x-axis, this can be positive or negative depending whether we are calculating the angle counterclockwise or clockwise. If we are calculating the angle counterclockwise, then the angle is positive, and if we are calculating the angle clockwise, then it is negative. Now let's consider an example. We are given this complex number 1 plus iota. Now let's see what is the position of this complex number in complex plane. Now x is 1 and y is 1, and the associated line segment is the following. Now we want to know the length and the direction, in other words the angle that this vector makes with positive x-axis. Now the modulus of this complex number can be calculated in the following way. So 1 square plus 1 square square root, which is equal to square root 2. So this is the length, or in other words the coordinate r of this complex number. Now let's see how to calculate this angle theta. Now the coordinates of this head of this vector are 1, 1. So in other words, this length is 1 and this length is also 1. Now we know that if we have this triangle, then theta is equal to pi by 4, or in other words 45 degrees. So we can say that theta is equal to pi by 4. So the polar representation of this complex number becomes z is equal to square root 2 cosine pi by 4 plus iota sine pi by 4. Now observe that we can also take the angle to be this one. Okay, so instead of taking angle to be pi by 4, we can take one round and then calculate this angle. So in other words, the angle that this vector makes with positive x-axis can also be taken to be pi by 4 plus 2 pi. And similarly, we can also consider the angle to be the following. So instead of going in the clockwise direction, we can also go in the counterclockwise direction. We can also go in the following way, so starting from this point and going in this direction. So in other words, we can also consider the angle to be pi by 4 minus 2 pi. And hence, we can also consider the following angles: pi by 4 plus 2n pi, where n is an integer. So we can say that for a complex number, the coordinate theta has infinite number of possible values, but all these values differ by integral multiples of 2 pi. Now, let's go further in the discussion of how to exactly find this coordinate theta. Now we know that theta is any value that satisfies these two relations. X is equal to r cosine theta, y is equal to r sine theta. So first we have the following definition to find out all those values that satisfies this relation. We name them as argument of a complex number. So argument of z are all those values theta that satisfies these relation, or in other words, for which z is equal to r cos theta plus iota sine theta. So we can say that argument of z is a set. Now, to single out one particular value of theta, mathematicians have agreed on one particular range of these angles, and this range is when theta lies between minus pi to pi. And we can see that here minus pi is not included. Theta lies between minus pi and pi, but we are allowed to be equal to pi but not equal to minus pi. So in other words, if we have this complex plane, then we calculate angle theta. We are allowed to go in this direction and we are allowed to be equal to this line, but from this direction we are not allowed to be equal to this line. And the values of theta for which theta lies in this interval are known as principal value of argument of z, or we just simply refer them as the argument of z. So we can say that argument of z is equal to the principal argument plus 2n pi, where n is any integer. Now let's see how to calculate the argument and principal argument of a complex number. So given a complex number, we have this associated vector, and associated to this vector we have the following right angle triangle. So this is the right angle in this triangle. Now this is the perpendicular, which is equal to the y coordinate, and this is the base of this triangle, which is the x coordinate of this complex number z equal to xy. Now if I want to know the value of this angle, then I can use the following relation. So tan theta is equal to y over x, and so theta is equal to tan inverse y over x. So this should give me the value of theta, but unfortunately there is another problem in this way of calculating theta. Now we can also see that tan theta is equal to y over x, but tan theta is also equal to minus y over minus x. So in other words, if I calculate the angle for this value of complex number, if I calculate this theta, then we will be getting the same value of theta. And this is due to the fact that function tan theta has period pi. So to solve this issue, we always observe that what is the quadrant of the complex number. So if it is the first quadrant, then of course theta must lie between 0 and pi by 2. And if it is the third quadrant, then it must lie between pi and 3 pi by 2. So here is the hint. Here is the solution of this problem. Observe the quadrant of complex number. So we can say that if given a complex number, then the argument of z is a subset of all those values which we have calculated using this tan inverse function. Now, based on these observations, we can state the following steps to find out the coordinate theta for a complex number. Now, in the first step, we see that if x is not equal to 0, so if x is not equal to 0, then we first calculate what is tan inverse y over x. And since the period of tan is pi, so we check the quadrant of this complex number and we find the angle by adding or subtracting multiples of pi. Now this is the value argument of z. Now further, if we want to find the principal value of argument of z, then we add or subtract multiples of 2 pi such that your angle theta lies in this interval. So these steps tell us how to calculate the theta coordinate or argument of a complex number. Now let's follow these steps to find out the polar representation of this complex number. Now the complex number is -1 minus iota. So the r coordinate can be calculated using the modulus of this z, which is equal to -1 square plus -1 square, which is equal to 1 plus 1, which is equal to square root 2. Now to find out theta, we have 3 steps to find out the argument of z. In the first step, we calculate what is tan inverse of y over x. So in this case, y is -1 and x is -1. So this is equal to tan inverse 1. Now if we use our calculator to calculate this value, then our calculator will give us pi by 4. So which is in fact in the first quadrant. This is the angle pi by 4. But observe that this complex number actually lies in the third quadrant. The coordinates are -1, -1. So it is in fact this complex number with coordinates -1, -1. So this is the second step where we observed the quadrant of this complex number. Now in the third step, we will add or subtract multiples of pi such that this angle lies in the third quadrant. Now if we add pi into pi by 4, then we will be in the third quadrant. So in other words, the argument of z, one of the values of argument of z becomes pi by 4 plus pi. Okay, so which is equal to 5 pi by 4. Now if we want to find out the principal value of argument of z, then we need to see that if this angle theta satisfies this relation, that is theta lies between minus pi and pi and not equal to minus pi. So observe that this theta, this value of argument of z lies in this interval. So we can say that the principal argument of z is equal to 5 pi by 4. Now if we are given r and the argument of z, the polar representation of this complex number becomes the following. So z is equal to square root 2 cosine 5 pi by 4 plus iota sine pi by 5 pi by 4. So far, we have imposed the condition that x should not be equal to 0. Now what happens if x is equal to 0? We cannot use this equation, this relation, since in this relation we are dividing y with x, and if x is 0, then this is undefined. So what do we do if x is equal to 0 and our complex number is non-zero? So remember, z is equal to 0, then we cannot calculate its polar representation. So z has to be non-zero. So if we are given that x is equal to 0, now what are the complex numbers that has x coordinate equal to 0? Now these are all the complex numbers that lie on y-axis. Now if x is on this side, in other words, if the imaginary value of z or the y coordinate of this complex number is greater than 0, then we take the argument of z to be pi by 2, since this angle is pi by 2. And if the imaginary value of this complex number is less than 0, in other words, we are on this side of y-axis, so we can say that the principal argument of z is basically minus pi by 2 or 3 pi by 2. So that's how we calculate the principal value of the argument of z when x coordinate is equal to 0. So as an example, consider this complex number. Now we can easily calculate the modulus of this complex number. So we can see that this is equal to 5. Now to calculate the principal argument of this complex number, we see that this is on the positive side. Okay, so 1, 2, 3, 4, 5. So we take principal argument of z to be equal to pi by 2. So this z has the following polar representation: 5 cosine pi by 2 plus iota sine pi by 2. So this is the polar representation of this complex number. So far we have learned what is the polar representation of a complex number and how to find this polar representation.